Hi, this is Antoine Couturier from the National Institute of Sport in France, and I'm going to show how EMG signals recorded from high-density electrodes array can be processed into Origin. So I've loaded raw data corresponding here to maximal voluntary contraction of the elbow flexors. I can enter here a window length that will be used later for computing RMS envelopes. So we have here all the raw data, and each channel can be marked as a lost channel with this button or as an innervation zone with this button. There's a scale button here that can switch back and forth from individual scales to common scales. Channel 48 is obviously a bad channel, so I remove it, and now it will be also removed from scaling. So individual scales and common scale. The analysis will be launched by clicking this calculus button. Each channel will be processed with a moving RMS window for which I entered the length earlier. Then, two FFTs will be run on each channel around min-maximal activity over a 200 and 500 millisecond window for computing mean and median power frequencies. So here we go. RMS envelopes, FFT analysis, and here is the report. This graph is the same that the first one we saw before. In this graph, we have the electrodes array displaying muscle RMS maximal activity in color map control graph. Next is mean RMS signal, which is the average of all the RMS EMGs. And this is the torque exerted by the subject. This line is movable. It is placed by default at maximal activity, but I can move it elsewhere, and the graph is updated. I can also animate the graphs with this button. Here, I can enter the step with which the line will be moved. Animation will play between these two lines. So I can make short animation like that. And I have to say that colors and animation are not looking very good right now. I guess I can blame it on the screen capture software. In these tables, we have a summary of the analysis. In this graph, we have, in addition to torque and mean RMS EMG, all the individual maximums when they occur and their corresponding channel. All the results can be dynamically updated if we mark channels as lost or innervation zone. For example, absolute maximum occurs in channel 27. If I set it as lost, you can see that it disappears from graphs and that the mean RMS signal is now a bit lower. I can further remove channel 44 or restore everything. A lost channel is completely removed from analysis and will be treated as missing value. When building the contour graph, it will be interpolated with Rinke-Klein algorithm, and center of gravity will be computed from this contour graph. The innervation zone, which is located here, is treated as missing value as well for analysis, but is kept for contour graph and center of gravity computing, as you can see. The FFT analysis is at the bottom of the report. We have color map contour graph of mean power frequency here and here, and median power frequency here and here. They are computed over 200 milliseconds and 500 millisecond windows centered at the maximal mean EMG activity. Mean values of mean and median frequencies are displayed here. Of course, all these graphs and values are also updated when marking a channel as lost or in inversion zone. This other book shows analysis for a maintenance exercise during which the subject has to maintain 70% of his maximal voluntary torque as long as possible. For this case, I won't show live analysis because it is quite longer. RMS envelopes are computed over signals lasting about 40 seconds, and more than 1,200 FFTs have to be done, so computing time is about 1 minute and a half. So we have again some graphs similar to those of the previous reports. And in this one, we have added all the local maximum EMGs, and the beginning and ending of the exercise is shown with these orange dashed lines. All the parameters are summarized here and are computed over periods of 5% of the maintenance time.